Welcome to lecture 25. So, this is the last lecture of the week, and this week we have been talking about unconstant single variable optimization methods and applications. So, we have talked about region elimination methods in last two lectures. Those methods did not use information on derivative of the functions. The methods used only function values. So, today we will discuss three methods which uses information on the derivative of the functions. There are methods which use only first derivative information. There are methods which use both first derivative and second derivative informations. So, let us look at the agenda today. So, we will talk about Newton-Raphson method, bisection method and secant method. So, we broadly we will cover two different types of methods: direct search methods, under which we talked about bracketing method and region elimination method, and today we will talk about methods requiring derivatives, and we will discuss Newton-Raphson method, bisection method and secant method. We do not want to claim that this is an exhaustive list of all the algorithms that are available. There are several other methods that are available. For example, successive quadratic approximation, cubic interpolations, etc. It will not be possible for us to cover each and every algorithm that may be used for solutions of unconstant single variable optimization problems, but we tried to cover most of the commonly used methods. So, let us now start our discussion on gradient based methods, and we will start with the Newton-Raphson method. So, the gradient based methods are more effective and more popular. However, it is not always easy to obtain derivative information for real life problems, because all functions or objective functions in a complex real life problem will not be a simple analytical functions like the ones we are discussing in these lectures. However, if derivative information is available, then the gradient based methods will be much faster compared to direct search methods. Analytical derivatives may not always be possible to obtain, and sometimes we will make use of numerical computations to obtain derivatives. There are various ways like central difference method, forward difference method, backward difference method, so on and so forth. So, when you make use of the gradient based methods, we know that the derivative at optimal point is equal to 0. So, that is how we obtain the stationary point. So, these methods, in these methods you will see that basically we are finding out the root of first derivative of the function. So, we set f prime of x equal to 0 and solve it. That means, we find the root of f prime x equal to 0 equation. Now, the fact that gradient equal to 0 at minimum point, in fact also at maximum point at stationary point, this gives us a termination criterion for the optimization algorithm. So, we can stop the search algorithm when the gradient or the derivative of the function is equal to 0. In actual practice, you may not hit exactly 0 value. So, we will define a small tolerance value and we will stop the algorithm when the gradient is less than this pre-specified tolerance value. So, now let us start with the Newton-Raphson method. Newton-Raphson method requires that the function be twice differentiable. So, we start with an initial estimate of the stationary point x 1, that is the initial estimate of the root f prime x equal to 0. Then a linear approximation of the function f prime x at the point x 1 is obtained, and the point at which the linear approximation is 0 is taken as the next improved approximation of the root of f prime x equal to 0. So, what we do is you start with an initial estimate of the root of f prime x equal to 0. So, you have given a function f x, you start with an initial estimate of the stationary point. Let us call that estimate is x 1. So, x 1 is the stationary point of the function f x is same as x 1 is root of f prime x equal to 0, where f prime x means first derivative of function f x. Then a linear approximation of the function f prime x at the point x 1 is obtained. How? By Taylor series expansion. And the point at which the linear approximation is 0, that means where this tangent line crosses the x axis, that point will be taken as the next improved approximation of the root of f prime x equal to 0. So, given a current estimate of stationary point x k, the linear approximation of the function f prime x at x k can be set to 0 to get next estimate. So, let us say that the current estimate of stationary point is x k. The function is f x and the current estimate of the stationary point is x k. That means, x k is also the estimate of root of f prime x. So, now let us expand f prime x in terms of Taylor series expansion and retain only the first order term, so that you get a linear approximation of f prime x at x k. So, this is precisely this. So, f prime x k plus f double prime into x minus x k is the linear approximation of f prime x. So, here this is f prime x function. At x k, you look at this tangent. This tangent is the linear approximation of the f prime x function at point x k, which is obtained by this Taylor series method. So, by setting this equal to 0, that means when this approximation touches this x axis, that means point x k plus 1, is the next improved guess for the root of f prime x equal to 0, and that can be obtained by setting this equal to 0, which if you rearrange you will get as x k plus 1 equal to x k minus f prime x k by f double prime x k. So, f prime is the single derivative, f double prime is the second order derivative. So, first derivative, second derivative, both the informations are required. Now, depending on the starting point and the nature of the function, it is possible that the Newton-Raphson method will diverge instead of converging to true stationary point. So, this is the expression that will be used iteratively to obtain better and better guess for f prime x equal to 0 or the stationary point of the given function. So, what will be the algorithm? We set initial guess equal to x 1, we set a small tolerance value, set iteration counter k equal to 1, compute the first derivative at this point S A x k, x 1 in the beginning. We also compute the second derivative. Then let us say I am at kth iteration. So, I have the current estimate as x k. So, this is the tangent to the function f prime x at point x k. So, this is the linear approximation. This crosses x equal to 0 at this point. This point is x k plus 1, which will be obtained as x k plus 1 equal to x k minus f prime x k divided by f double prime x k. Now, you compute the first derivative at x k plus 1. If this first derivative is less then the pre-specified tolerance will stop, because we will assume that the derivative has become very close to 0. Note that you have to take the absolute value of the derivative. Otherwise, if we consider epsilon is greater than 0, and large negative derivative will also be small than a small positive value. So, you will always consider the absolute value of the gradient for stopping criterion. So, if the first absolute value of the first derivative is less than the set tolerance value, we stop, else we set k equal to k plus 1 and go to the next improved trial point by computing it as x k plus 1 equal to x k minus f prime x k by f double prime x k. So, as it is shown here, we have obtained the x k plus 1 and then at x k plus 1 we again make the linear approximation of the function f prime x. So, that touches the x axis at x k plus 2. So, x k plus 2 is the next improved estimate for the stationary point of the function f x or the root of f prime x equal to 0. So, this way we will proceed till convergence, and the convergence check is absolute value of the first derivative has to be very small, ideally 0, but it has to be very, very small in practice. Sometimes we have to make use of numerical derivatives. Several expressions are available. Here we are showing the expressions obtained using central difference method. So, f prime x equal to f of x plus h minus f of x minus h by 2 h. So, you have the point x, you consider h. So, you obtain the function value values at x plus h and x minus h, get the difference and divide it by 2 h. Similarly, you can also have the second derivative. Now, let us take an example, f x equal to x square plus 30 by x. This equation we have used before as well. We know the minimum is bracketed somewhere between 2 to 3. So, let us now try to solve this problem using Newton-Raphson method. Let us start with an initial case x 1 equal to 2. So, we first find out first derivative and then we find out second derivative. So, at x 1 equal to 2, the first derivative is minus 3.5, second derivative is 9.5. So, the next improved point x 2 will be obtained as x 2 equal to x 1 minus f prime at x 1 divided by f double prime at x 1, which is obtained as 2.3684. In the second step, we have the initial case as or the starting point as 2.3684. So, we find out the first derivative and second derivative at this point and obtain the next improved point x 3 as x 2 minus f prime x 2 divided by f double prime x 2, which is obtained as 2.4622. Note that this is very close to the true stationary point. In the step 3, we have x 3 equal to 2.4622. We evaluate the first derivative and second derivative. See, the first derivative is minus 0.0241, which has become small. So, x 4 can be obtained now as x 3 minus f prime x 3 by f double prime x 3, which is obtained as 2.4662. Now, you can go to step 4 and get even closer to the true optimal solution. Note that the absolute value of f prime x 3 at this stage is 0.0241. So, if we would have set epsilon as let us say 0.25, I would have stopped at this point. But if we have set say epsilon equal to 0.01, we must go to the step 4 or iteration 4 to check whether the convergence is achieved or not. So, this way you can make use of Newton-Raphson method for minimization of a function. Next, let us talk about bisection method. The bisection method uses function value and sign of first derivative at 2 points to eliminate a part of search space. It does not use second derivative. Unimodality of the function is assumed. So, in some sense bisection method is similar to the region elimination method. In case of region elimination method, the function values were used at 2 different points within the interval to delete a part of the region. In case of bisection point method, we make use of the first derivative information, more specifically sign of the first derivative information to delete a part of the region. Contrary to Newton-Raphson method, it does not use second derivative information. Newton-Raphson method we have seen, it uses the first derivative and second derivative information. The bisection method uses only first derivative information, in fact the sign of the first derivative information. So, let us see how it works. At the maximum or minimum of a function f prime x equal to 0, at maximum or minimum of a function we know that f prime x equal to 0, that is the stationary condition, that is the condition to obtain stationary point. Since the function is assumed to be unimodal, the gradient of the function changes sign near the optimum point. So, the sign of the gradient at optimal point is actually the numerical value of the gradient at the optimal point is 0. So, if we keep track of the sign of the gradient must have changed from say 0, some positive to 0 and then negative. So, around the optimal point there will be change in the sign in the gradient. So, to start with we will consider 2 points say A and B such that the gradient at f A is positive, then gradient at f B is negative. So, if this is the case, we know that the minimum has been bracketed between A and B. And if I take a product of f prime A and f prime B, and if this product is less than 0, I know that one of these f prime A or f prime B is negative, another one is positive. So, we have to take 2 points A and B such that the first derivative at these 2 points have opposite signs. In that case, the minimum has been bracketed between A and B. This happens because the gradient changes its sign around the optimal point. So, if the gradient was positive at A, it will become negative at B. So, it must have crossed 0 in between, because the function is unimodal. So, if f prime x 1 and f prime x 2 are the derivatives of a function computed at points x 1 and x 2, then the minimum of the function is bracketed between x 1 and x 2 if the sign of f prime x 1 and f prime x 2 are different. One is positive and the other is negative, and the check will be f prime x 1 into f prime x 2 is less than 0. So, let us look at the algorithm. We first choose 2 points A, B such that f prime A is less than 0 and f prime B is greater than 0. So, the sign of the derivatives must be opposite at these 2 points. Then we know the minimum lies between A and B. So, now we set x 1 equal to A and set x 2 equal to B. We also set a small tolerance value. Now, let us compute the midpoint x 1 plus x 2 by 2. Evaluate the first derivative at this midpoint. If the value of this first derivative or absolute value of the first derivative is less than tolerance, we have achieved convergence, so stop. Else, if the first derivative at this midpoint is less than 0, then what happens is we will eliminate one part, and if the first derivative at z is greater than 0, we will eliminate the other part. So, looking at the sign of the derivative at z, looking at the sign of the first derivative at z, we will either eliminate one part or the another. After that, we again find out the midpoint of the remaining interval and continue in the same fashion. So, now let us look at the figure to understand it better. So, this is the function and this is the first derivative of the function. So, the minimum is bracketed between point A and point B. So, I set x 1 equal to A, x 2 equal to B. I obtain the midpoint z as x 1 plus x 2 by 2. Now, if the derivative, to be particular, if the first derivative at z is negative, we will eliminate the left half, because if the derivative at the midpoint is negative, the minimum cannot lie on the left half. So, we will eliminate the left half. You can also realize it from the figure. Similarly, if the derivative is positive, the minimum cannot lie on the right side of midpoint z. So, in that case, we will eliminate the right half z b. So, depending on which part you eliminate, you set either x 1 equal to z or x 2 equal to z. In the figure shown, at z the derivative is negative. So, we will eliminate the left half and we will set x 1 equal to z. So, this will be my interval in the next iteration. So, again you will take a midpoint of z b and continue as shown. After bisection method, let us talk about the second method. In the bisection method, you used only the sign of the derivative to locate the 0 of f prime x or to locate the stationary point of the function f x. In the second method, both the magnitude and the sign of the derivative are used to locate 0 of f prime x. So, in case of bisection method, we have used the sign of first derivative only. In case of second method, we use both sign of the first derivative as well as magnitude of the first derivative to find out the stationary point of f x or to find out the root of f prime x equal to 0. So, again we start with 2 point x 1 and x 2 such that f prime x 1 and f prime x 2 have opposite sign. In other words, f prime x 1 into f prime x 2 is less than 0. That means, the minimum is bracketed between x 1 and x 2. Next, we assume that f prime x varies linearly between points x 1 and x 2. So, we assume that f prime x varies linearly between points x 1 and x 2. So, a second line is drawn between points x 1 and x 2. So, that line is an approximation to f prime x between x 1 and x 2. The point z where the second line crosses x axis is taken as the improved guess for the 0 of f prime x in the next iteration. The point z where the second line crosses the x axis is taken as the improved guess for the 0 of f prime x in the next iteration. One of the points x 1 or x 2 is then replaced by z using sign of f prime z, and either x 1 z or z x 2 is eliminated. We can do this the same way we have done it in case of bisection method. It may be noted here that more than half the search space or smaller than half the search space may be eliminated at a particular iteration. So, where is the algorithm? The algorithm is basically same as the bisection method. The only change is in the computation of point z. In case of bisection method, the point z was taken as the midpoint of the interval, but here the point z is where the second line crosses the x axis, and that can be computed from the magnitude of the first derivative at point x 1 and x 2. So, we choose 2 points a and b such that f prime a and f prime b equal to 0. So, I have chosen point a and point b, and you note that at point a f prime a is negative and at point b f prime b is positive. So, the minimum lie between a and b. So, we set x 1 equal to a and x 2 equal to b. We also define a small tolerance value. Now, I draw the second line. So, this is the second line, and the second line crosses the x axis at z. So, this z is basically the solution of the second line and the x axis, the crossing point. So, that can be obtained as z equal to x 2 minus f prime at x 2 divided by f prime x 2 minus f prime x 1 divided by x 2 minus x 1. So, this is the expression by which you can obtain z. So, evaluate the first derivative at this point z. If the absolute value of this first derivative at z is less than the tolerance value, we stop. Otherwise, if f prime z is less than 0, we will set x 1 equal to z, because then we will eliminate the left half. So, this is shown in the figure. The f prime z is negative. So, the minimum will not lie here. So, the left half of z is eliminated, and we set x 1 equal to z and go to step 2, x 1 equal to z and b is set at x 2 and we will go to the next step to compute z. If f prime z is greater than 0, we will eliminate the right hand part and set z equal to x 2 or x 2 equal to z, and then we will go to the step 2 where we compute z as x 2 minus f prime by f prime x 2 minus f prime x 1 divided by x 2 minus x 1. So, this way we can solve a problem using second method. Note that this is exactly same as bisection method, except the computation of z, otherwise the algorithm is same. So, here is an exercise. We have solved this function x square plus 30 by x using Newton-Raphson method. We have also solved this using region elimination method. Please try to solve using bisection method and second method and compare your results with the results obtained using Newton-Raphson method. Note that the minimum will lie between 2 to 3, around 2.5 value we obtain using Newton-Raphson method. So, with this we will close lecture 25 and our discussion on single variable unconstrained optimization methods.